I'm honored to be here, and my goal is to be sure that you understand the title by the end of the talk. So, differential privacy is a definition of privacy, and it's tailored to the statistical analysis of large data sets. The research effort leading to the definition and the mathematical techniques to support it began in the early 2000s. And the US Census Bureau analyzes the people's data in order to allocate the people's resources for the benefit of the people. And this scenario was a strong motivating force for us. It was the driving force. And one reason is that United States law requires that census responses be held confidential. So there was a legal mandate for privacy. Okay. So I'm going to use the term data analysis very loosely. You can think of data analysis as just a function, if you're a mathematician, or a program that takes data of arbitrary types and produces an output. And the algorithm, the analysis, can flip coins. It can make random choices. So the kinds of data that could feed in could be medical data, social data, news, Wikipedia pages, music, art, code, a mail corpus, and so on. And what's produced could be a recommendation system. It could be something for predicting whether an individual will repay a loan. It could be a large language model. Or it could be some kind of analysis of DNA that looks for a location in the DNA that seems to be strongly correlated with smoking. And a natural question to ask is whether in statistical data analysis, one's data can actually be detected. So I was very vague about what this function or program F did, and one of the things that F could do is simply output some of the data that it took in as input. But in a more interesting way, maybe it outputs ChatGPT. Well, does ChatGPT actually produce some of its training data? It turns out that yes, this happens. So for example, this 2023 paper describes a prompting strategy, that is a way of questioning the language model, ChatGPT in this case, that causes them to reveal verbatim huge quantities of the data on which it was trained. So concretely, in one instance described in the paper, ChatGPT revealed a person's email signature, which included their personal contact information. Well, you say, what if we only looked at analyses that produced statistics? So let's restrict our analysis to revealing statistics. Statistics feel private. A statistic is a quantity that is computed from a sample, and yet it is supposed to tell us about the population as a whole. Two data sets that are collected independently from the same population and with proper sampling methodology really should tell us essentially the same things. That this is why the field of statistics actually works. It doesn't matter which sample you use, just a well-chosen sample, a proper randomly chosen sample, should tell you about the population. And our sense of privacy for a statistic comes from this fact. So you might think, if you're selected for the sample, nobody knows that I'm in the sample, or the results would be the same even if I opted out, or again, even if an entirely different sample had been chosen. So this intuition is on the right track, but it's mathematically flawed and it needs some help. Differential privacy will provide that help. Differential privacy will actually preserve this notion of I could have opted out privacy for every computation, including total computation counts, total population counts. So let's consider the personal information of whether or not one flosses one's teeth regularly. Okay. And let's consider some statistics. So maybe we ask the question, how many Los Angeles Dodgers players floss their teeth regularly? And we get the exact answer for that. But it's a total population count, and even if it's not, let's say it's half the players or 3/4 of the players, we don't know who is in the set that flosses and who is in the set that doesn't. But if we got to ask a follow-up question, how many Los Angeles Dodgers players other than Shohei Ohtani floss regularly, and we have the exact answers to the two of those, we can subtract one from the other, and we could learn how well he takes care of his teeth. So this is a special case of an accumulation of privacy loss that happens when many statistics are released. And this accumulation of risk is captured by what we call sometimes the fundamental law of information recovery or the database reconstruction theorem. And this mathematical law says intuitively that overly accurate estimates of too many statistics completely destroys privacy. No matter how one attempts to blunt the attack by introducing some inaccuracies, there's a hard limit on the number of measurements before privacy is completely destroyed. And that limit is tied to the accuracy. Just as the number of medical images that can safely be taken depends on the dosage of radiation in each of the images. So, for example, you can safely have more dental x-rays than you can have mammograms. Here's another case where statistics are crucial. I mentioned the US decennial census. So every decade, the United States government carries out a complete enumeration or count of the people living in the United States. The enumerated populations in each state serve as the basis for allocation of hundreds of billions of dollars in federal money, the drawing of congressional districts and the enforcement of the Voting Rights Act, the apportionment of the 435 congressional seats in the House of Representatives. So how many representatives are allocated to each of the different states? The drawing of legislative districts in all states, and it informs myriad commercial and government decisions. So what kind of harms could happen if census data are not properly protected, if their confidentiality is not properly protected? Section 8 housing units are federally subsidized housing units. And people wait years, sometimes even more than a decade, for federally subsidized housing. And the housing comes with a lease, and the lease specifies how many people can legally live there. So Section 8 housing units with the number of occupants that are in violation of the lease agreements, if that information is leaked, somebody could be evicted after waiting a decade for the housing. Or maybe in the 2020 census, somebody reported a child living in the house as a 13-year-old girl, and in the 2010 census, they reported a 3-year-old boy. In this case, the parents could be prosecuted for supporting the gender self-identity of the child in some states. And another thing that could happen if confidentiality is not properly protected is that somebody that lives completely in a different part of the country could compile a list of all of the gay married couples in the United States, resulting in doxing and harassment of gay people. And I want to point out that when something like this third case happens, this is not a case of my neighbors already know that I'm gay. Your neighbors know that you're gay because you felt comfortable living in that neighborhood. You chose this neighborhood as a place to live. And that doesn't mean that you would tell people that you don't know and that who have an animus against homosexuals that you're gay and that live somebody completely different. So there can be very real harms even on the basis of rather straightforward and not very detailed census data. And confidentiality is viewed as of primary importance in the census because they feel that if people don't trust that their data will be held in confidence, then they simply won't answer the census. And the US law requires confidentiality. To give you a sense of scale, in 2010, the Census Bureau published 7.7 billion linearly independent statistics on the data of merely 308.7 million people. So Census carried out its own reconstruction and re-identification attack on the 2010 data release. And of all of the tables that they published for the attack, they only used 34 of the tables. And because they knew the ground truth, because they actually had the true census responses, they were able to evaluate how well they had done in the attack. So their conclusion was, in the words of John Abowd, the former chief scientist at the Census Bureau, that technical advances revealed a new vulnerability, allowing people to reconstruct data from tables that were previously assumed to be privacy-preserving. So what they did was they reconstructed records based on these statistics, and the reconstructed records had fields of census block, which is a geographic location, the sex, the age, the race, and the ethnicity for everybody in the Census Bureau. Now, they weren't all correct, but they made a list of all 308 million records. Those records have no names. They then linked these records to commercially available data sets, which do have names, and the linkage was done on common fields like age and address, or census block. And what they found boiled down to correctly re-identifying the records of 52 million people, or 17% of the population. And the privacy violations there were considered to be the ethnicity and the race. And one of the things that the Census Bureau pointed out is when you learn, for example, that a child has different race than both of its parents, you can deduce that the child was probably adopted. And that's a major privacy compromise. So that's the problem that we want to deal with. And in order to do so, in order to turn it into something that we can address with mathematics, we need to abstract the problem. So this is a picture of Henrietta Swan Leavitt, famous for measuring distances across space using a relation that she observed between certain variable stars' peak brightness and the period of time over which their brightness varied. So here we have a database, and we have the records of Henrietta Swan Leavitt, and we want to know what kind of a privacy guarantee could we possibly offer her. So the first thing that came to mind was actually, it's the first thing I tried, but it was a definition, it turned out, that was quite a bit older, posed in 1977 by the statistician Tordellinius, which says essentially that the data analyst shouldn't be able to learn anything new about Levitt that the analyst didn't know before interacting with the data set. So Levitt might be a public figure, she might be an extrovert, there could be all sorts of information about her in the newspapers and so on, but by interacting with the confidential data set, the analyst shouldn't be able to learn anything that wasn't already public. So that might be a kind of guarantee that we would like to offer. And the problem with that is sort of, well, what's the point in that case? So let me be more specific. Let's suppose that I'm from Mars, and I believe that all human beings have 2 left feet. So in particular, I believe that Levitt has 2 left feet. And I interact with a statistical data set, and I learn that the vast majority of humans have 1 left foot and 1 right foot. And so my beliefs about Levitt have now changed. And I think that in all likelihood, she had 1 left foot and 1 right foot. So the question is, has her privacy been compromised? I've learned something new about her that I didn't know before. Has her privacy been compromised? How many people think it has? Good. So we agree. But it's a judgment call. We decided that we were not going to call this a privacy violation. And part of the reason was, well, we would have learned the same things even if Levitt had been replaced by another random member of the population. And this is Cecilia Helena Payne Gaposchkin. She was famous for discovering that the sun and the earth, or more generally, the earth and the stars, do not at all have the same composition. They have very different amounts of hydrogen. She was also the first person to get a PhD in astronomy at Harvard. So this brings us to the English language definition of differential privacy. It says that the outcome of any analysis is essentially equally likely independent of whether any individual joins or refrains from joining the data set. Now the question is, when I say essentially equally likely, that says there's some uncertainty. So where is this uncertainty coming from? And the answer is that our algorithms are going to flip coins. They're going to deliberately introduce some randomness in order to hide the presence or absence of any individual or small number of individuals. Just a little bit of an analogy here. Suppose I have 2 coins. One of them is a perfectly fair coin, so chance 50 over 100 of coming up heads if I flip it. And the other coin is slightly biased, 51 over 100 chance of coming up heads. So let's suppose that I'm going to flip a coin, and you don't know which coin. You know the 2 possibilities. You know it's either a fair coin or 51 over 100, but you don't know which one I've chosen. And I flip the coin, and we get an outcome. So given one or even several flip outcomes, you can never have confidence in terms of figuring out which coin I actually flipped, because the outcome was essentially equally likely in the 2 cases. So here we have 2 data sets. The 2 data sets are identical, except one of them has the data of just one more person, Gaposchkin. And the analyst is interacting with one of these data sets through a differentially private mechanism. And even if the analyst knows both data sets, she should not be able to tell which one was the actual data set being used. Just like you knowing both of the coins based on a couple of flips can't tell which coin I actually flipped. Data sets that differ in the data of just one person are called adjacent data sets. And now we can give the formal definition of differential privacy. This is the only equation. Again, the English language version is that the outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. So let's say that we have two data sets, X and Y. They are adjacent, meaning they're almost identical, but one has the data of just one more person. The definition is completely symmetric. I can switch the roles of X and Y, and this inequality has to hold. And what this says is that the probability of observing any particular event is essentially equally likely, where the randomness is introduced by the algorithm, whether the data set is X or an adjacent Y. And essentially equally likely here is measured by this term e to the epsilon. Epsilon is a privacy parameter. It is public, it is publicly known, and it's chosen by the person who is implementing the algorithm. And if you're not familiar with this form, e to the epsilon is approximately 1 plus epsilon when epsilon is small. So it says that these two probabilities, the probability of observing the event S when the data set is X versus when the data set is adjacent Y, are almost the same. Reformulating, suppose X is the data set that doesn't contain your data, and Y is identical, but your data have, other way around, sorry. Let's make X be the data set that contains you and Y the one that doesn't. So your intuition is a data set that doesn't contain you can't leak any information about you, so this term on the right is going to be very small. And what this says is that anything that can be learned about you when you are there, when it's X, should be learnable about you even if you've opted out and the data set is actually Y. Now, I'm not saying that there's never any harm in statistical analysis. So let's suppose that we have a medical data set and it teaches us that smoking causes cancer. So a smoker might be harmed in the sense that their insurance premiums might go up and they might have to pay more for health insurance. Okay? But the differential privacy will ensure that the same things would be learned whether this smoker is or is not in the data set. So differential privacy lets us separate the harms that come from the teachings of the data set or from the population as a whole from any harm that could happen as a result of participating in a medical study. Now, learning that smoking causes cancer is the entire point of medical research. And now the smoker can change her habits or enroll in a smoking cessation program in order to benefit from these teachings. So differential privacy will, we hope, encourage people to allow their data to be used because the benefits of science can be increased without harming the privacy of the individual participants. So differential privacy supports science. Now, there are certain nice properties that follow from the definition, independent of how one actually implements differential privacy. And one of them is being future-proof or resistance to post-processing. And it says that the ability to figure out whether somebody was included or not doesn't change when an adversary learns more information from other sources. Just as with that coin, you don't know which one was flipped, no matter what other things you learn about coins and the metal that they're composed of and things like that. So it's resilient to present or future information from other sources. It also composes gracefully and automatically, and by that what we mean is that we can understand the accumulated privacy loss over multiple adaptively chosen computations. We know, for example, that at worst the privacy losses, the epsilons, add up, But we know a lot more than that, and how often one can do much better than just adding up the epsilons. And when we take these two together, we learn that what we can do is we can create differentially private algorithms made up of small differentially private building blocks, or primitives. And so differential privacy is programmable. We can track how privacy loss accumulates, and we can build algorithms made of differentially private pieces and control their privacy losses so that we get the accumulation that we can live with. There is no other theory that has these properties, and this is why it's successful. How much time do I have? Somebody? Okay. I'm going to proceed then. I want to give you just one example of a technique, which is symmetric noise addition. So suppose you want to know what is the population of Washington, D.C. Now, in 2010, they were not using differential privacy, so we have an exact enumeration from 2010, and the answer there is 601,723. So I have a number line here, and I've got the true answer marked with a red star. Now, if one person were to opt out of the data set or fail to respond to the census, then the count would look like 601,722. And so what we are going to do, because we want to obscure whether any individual opted in or opted out, is we want to add some noise to the true count in order to obscure the difference between 601,722 and 601,723. So this is my attempt to draw a symmetric curve. I'm not very good at drawing. So this is the probability distribution on outcomes. The most likely outcome will be the truth, and then as we get farther away from the truth, larger or smaller, the probabilities will drop off. So the question is, how fat should that hump in the middle be? How spread out should those two distributions be? So there are two key parameters to determining the answer to this. One is, how much can the data of one person affect the count? That's called the sensitivity, and it's denoted delta. Since it's just counting, any individual can affect the count by at most 1. If you opt in, you increase the count by 1. If you opt out, you decrease it by 1. The other question is, how tightly do we wish to control the privacy loss? Remember I said that epsilon is chosen. It's a parameter and it's a design choice. So one might say, oh, I want privacy loss to be very, very small. So that might correspond to an epsilon of 0.01. Or maybe somebody's much more relaxed and they say, oh, I'm happy with epsilon being 1/10 or even 1 or something. So those are the two key quantities. And the right answer is that the width of the curve, sort of like the standard deviation, should scale with the sensitivity divided by the privacy parameter. So a larger sensitivity, meaning one person's data can really swing the outcome a lot, says we need a fatter curve. And there's delta sitting there in the numerator, so when it's bigger, the curve is going to be fatter. Privacy, if we don't have much privacy concern, then the distribution can be centered very tightly around the truth. But if the privacy concern is high and we want to make sure that we have really good privacy protection, then we want epsilon to be very small. And there it sits in the denominator. So when it's smaller, the curve again is going to be fatter. And the exact answer is we use a Laplace distribution with parameter delta over epsilon. But the intuition is in the previous. So only the coins are secret. The methods are public. The exact distribution on the noise is public. Everything is public. The code is public. The only thing that has to be secret is exactly what is the draw from the random distribution, from the Laplace. And that's all we need to make it private. So you can think of differential privacy as blurring a picture. The overall scene is clear, but the details have been fuzzed. So you should think maybe about Monet or an Impressionist art. And the question is, which picture is more true? So it turns out that differential privacy, mathematically, is a stability notion. If you change the data set a little bit, you should not get much change in the outcome. This turns out to be essential for machine learning and AI. And so again, which one is more true? Okay, thank you.